Hello, hello.
Hello, hello. Yes, it is visible.
Okay, so I think we can start. I guess no one else will join. Okay, so I think we can start. Today we will discuss about number theory and bit manipulation. So basically, you don't get problems on number theory in interviews very often, to be very honest. But you get problems on number theory in online assessment in online assessment rounds, also in various CP contests. So you can't ignore number theory first of all, because the first step is online assessment, and in online assessment there is a high chance that a problem from number theory will come, because there's a high chance. I am saying that there is a high chance because they don't ask problems on number theory in interviews, right? So there's a high chance that a problem might come in online assessment rounds. Okay, so the advantage in number theory is that there is not a lot of topics there. There are only 2 3 topics, like the Sieve and the Euclidean algorithm. So if you learn this 2 or 3 topics, you can solve most of the problems from number theory. So today I guess we will discuss about Euclidean and Sieve, about Sieve of Eratosthenes, and after that we will also discuss about bit manipulation. So bit manipulation is very important because it is asked in interviews or as well as in online assessments. Okay, so bit manipulation do have a lot of topics, but here we will see or discuss some of the most common or some of the most important topics. Okay, so first of all, we will start with Euclidean algorithm. Uh, what is the spelling of? Okay, so basically, Euclidean algorithm is used to find the GCD of two numbers. So So can anyone tell what approach or what algorithm can we use for finding the GCD of two numbers? Like it can be in any complexity. Like what is the brute force complexity of finding the GCD of two numbers? Can anyone tell? Like I want it to be a interactive session. Like it should be a two-way traffic, not a one-way traffic. Anyone? Like no one.
We will search for a number mm, to find the GCT. Which one is the highest number?
And then
The highest number which can be GCD of with another number.
like if you are given A and B, how would you start the algorithm, or how would you design the algorithm?
Um,
Like,
yeah, am I audible?
yeah,
Yes, so I have a naive approach that we should traverse over the factors of both A and B, and then the highest common factor which we find, we should output it.
yeah.
This is
So what will be the time complexity of that?
like it should be of n by 2, but if we only traverse over the normal factors up to root n, then that should be O of root n.
Okay, so basically you can find the Euclidean algorithm. Sorry, you can find the GCD in O of root n, right? Okay, so that's a good approach. It's not a naive approach. First of all, the naive approach is in O of n, so it is a better approach or an optimized approach. What you told in O of root n. So we will also discuss about how to find factors in root n. Okay, so many of you might not know like how to find factors in root n. Okay, so first discuss about finding factors, then we can go to this algorithm. Okay, so for means how to find factors of a number in root n time. So someone was telling about root n. So Biprodeep, can you please like elaborate like how would you find the factors in root n?
Yeah. We can, there is a common observation that if there is a factor of a number, like it should always occur in pairs. Like
Yeah.
suppose the factor of 12 should be 2 times 6 or 3 times 4. And if the number is a perfect square, then the means the last number we should iterate on is root of n. Like root of n into root of n is gives me n. So up to root of n, all the factors must exist, and the other factor should be like n of I, n by I.
Yes, exactly. So what he told is perfect. Like if you take a number, let's say we take 32. Okay. So one thing is what one common observation is that factors always come in pairs. Okay. So what do I mean by that? Factors always come in pairs. So if a is a factor of 32, then 32 by a will also be a factor of 32. Is this clear? Like if a is a factor of 32, so 32 by a will always also be a factor of 32. Okay, so if we find a, we will automatically find this. So is this clear? Like this part, what I told just now, the pair thing. Yes or no? Like instead of writing in the chat, you can just speak up. Okay, so yeah, so so if we know a, we can easily find out 32 by a, right? So how far can a go? Like, so if we are checking for 32, 1 is a factor of 32. So 32 by 1, that is 32 is also a factor of 32, right? So next we go to 2. 2 is a factor of 32. So 32 by 2, that is 16, will also be a factor of 32. Next we go to 3. 3 is not a factor, so we skip. 4 is a factor. So 32 by 4, that is 8, will also be a factor. Next we go to 5. 5 is not a factor. 6 is not a factor. 7 is not a factor. 8. Okay. 8 is a factor. But see that we have already considered 8 here. So do we need to check numbers from 8? Think once, or means do we have to check after the numbers after 8, or means from 8? Like do we have to check numbers from 8 to 32? Yes, like do we have to check? Is it necessary to check the numbers after 8? Exactly, because if we take 8, so the pair of 8 is 4, but we have already found out this pair, so there is no point in continuing after this. Okay, so we have considered only till 4. Okay, so what is the square root of 32? Is roughly around 5 point something, right? So uh, this first number in the pair can go up to maximum of 5. Okay, because let's say there is a number greater than 5. Let's say x is greater than 5. So 32 by x should be less than 5, right? Till this, is it clear? So if x is greater than 5, so what I'm trying to say is that if one factor is greater than root of n, so the other factor will be less than root of n, right? Uh, so we don't need to check the factors which are greater than root of n, because we will already get or we will automatically find them in pair of those factors which are less than root of n. For example, if we take this factor which is less than root of n, we will already find x. Okay, so we need to check every number from 1 to root n, and if that number, if x is a factor of n, so that is if n mod x is 0, that is n is a factor of x is a factor of n. So the factors are, so means the two factors are uh, x and n by x. So these two are the factors. Like this we can find out the factors of a number in root of n. Okay, so is this clear? So finding factors in root n, you can find now if there is a question like find the factors of a number in root n. So if the interviewer asks you, so you can tell this approach. So this is currently the best approach like for finding the factors of a particular number. So I think nobody has any problem in this. So we can go to the next part, like the GCD one, Euclidean part. Okay, so now we go to the next part, that is the Euclidean algorithm. So this one finds the GCD of A and B. Okay, so let's take an example. Okay, so we are finding the, oh okay, so what someone said, probably Biprodeep, I guess. So he said he can find the GCD of A and B in root n. So what he will do is that he will find the factors of A in root A time, and he will find the factors of B in root B time. So and he will take the highest common factor out of all those factors, right? Biprodeep, am I right? Is that was your approach, right?
Yeah, yeah,
Yeah.
yes.
So this will go up to root of root of maximum A comma B. Okay, so this is a good approach, but we can do better. Okay, so how we can do better? Uh, the most important observation here is that GCD of A comma B, let's say let's for means convenience, let's take A is greater than B. Okay, so if this is not the case, like if A is less than equals to B, we can swap A and B. Okay, so let's, for the sake of convenience, let's take A is greater than equals to B. Okay, so the most crucial observation here is that GCD of A and B is equal to the GCD of A minus B comma B. Now is this clear? Means how can it means can anyone prove that how this is coming? Like how this holds true? Anyone, like any example?
Like this one holds like an example can be 24 and 16. Like
Okay.
the GCD is 8.
Yeah.
So so if I do like A minus B, so it will be 8 comma 16, and then we can swap both of them, and then again this will go for 8 comma 8, and then it will go for 0 comma 8, and when it's 0, so it will be 8. So we will get the right answer. So
Yeah, that is one example, but can anyone get any intuition like why this is working?
By contradiction, we can find like
Okay, so
a.
but just 1 minute, I forgot to tell one thing. Like GCD of 0 comma A is 0 A, right? Okay, this everyone will agree. GCD of 0 and any other number is that number, because 0 is divisible by A and A is also divisible by A. So, yeah. Okay. So anyone was telling about contradiction.
Yes, Bhaiya. Actually, we can take A equal to K into P. and b equal to k into q, where k is the GCD and p and q will be relatively prime because k is
B
the
is equal
GCD.
to K1 into Q, right?
Q, not
Q
k
is
into
the
q.
GCD.
A equal to k into p and b equal to k into q. K into q, b equal to k into q.
And A is K into P.
P.
Yeah.
So k
And
is here GCD and then p and q will be relatively prime
yeah,
because k is the GCD.
yes.
Then we can take that to a minus b comma b. So that will be
So
k
A minus B will be P
k into
minus Q.
p minus q,
So this is
and
also divisible by K, right?
yeah,
Yeah.
and
So
then
this is the thing. So I was looking for this proof only. So let's take A is K into P and B is K into Q, where K is the GCD. So like A minus B will be K into P minus Q. So as you can see here is that A minus B is also divisible by K. So the GCD of A minus B comma B is equal to GCD of A comma B. It is also equal to the GCD of A minus B comma A. Okay. So since we have got this formula or observation, we can build on this. So like if GCD of A comma B is equal to the GCD of A minus B comma B, so it will also be equal to GCD of A minus 2 into B comma B, right? And this will go on like this, like GCD of A minus Z into B comma B, where A minus, sorry, A Z is A by B, right? It's the floor value, okay? So this equation is clear to everyone. Yes or no? Like how this one came. Yeah. So can anyone tell like how can we rewrite A minus Z into B as?
a modulo b.
Perfect. So A minus Z into B is nothing but A modulo B. Uh, because when you are subtracting Z into B, the thing that is left is the remainder when A is divided by B. So let's take A equals to 13 and B equals to 5. Okay. So what will be Z? Z will be 2. That is 13 by 5. If we take the float value, it will be 2. So A minus Z into B will be 3, and which is also equal to 13 mod 5. Okay, so it's equal to A mod B, right? So is this clear? Like if anyone has any problem, like he or she can tell. Yeah, so what we have got, so GCD of A comma B equals to GCD of A mod B comma B. Sorry, yeah, right? This we have got. So now means can anyone realize that how much we have improved the time complexity?
Like it has now become of log complexity, since we are
Yeah,
dividing, almost dividing, like
yes,
we are taking out the
because
remainder every time.
every time we are dividing A by B, so it has now come, the complexity has been reduced to log of A comma B, that is minimum of A comma B. Okay, because every time we are dividing A by B, okay, so A will be means if in the first iteration the value of a is x, in the second iteration it will be a minimum of x, means it the value will be reduced to a maximum of x by 2. So in the second iteration the value of a will range from 0 to x by 2. Okay, so in every iteration the value of a is reduced by at least half. Okay, so the number of iterations it will take to come down to 0 will be log base 2 n, sorry, base a, right? And since here we have considered a, means the minimum as a, so we are taking a. So if b was the minimum, we would have taken b instead of a. So the time complexity is log base 2 minimum of a comma b. Okay, so is this thing clear?
Yeah, here we are taken like A is the maximum one. So is it maximum of A or B, or we should take it as B?
Oh, sorry, I'm very sorry. It should be maximum, not minimum. Yeah. So yeah, we have taken a as maximum here. I forgot. Yeah, a is the maximum. Very sorry. So the maximum value is getting reduced to half in every iteration, right? So the time complexity is log 2 maximum a comma b. Since here the maximum is a, so the time complexity will be log base 2a. If the maximum was b, instead of here a, we would have written b. So like this. Yeah, that was a good catch. So I missed that. So it will be log 2 maximum a comma b. So we have reduced the time complexity from root n, sorry, root a to log a. Okay. So this is currently the best approach for finding the GCD of a number. Okay. So there are other uses of this algorithm as well. So I think we don't have enough time to discuss all that here, but you can definitely go to CP algorithms or GFG. Like there is a algorithm called extended Euclidean algorithm. So it is used to find the coefficients of a linear equation. Okay, so you can use that, but I don't think it will be asked in interviews, uh, because that has a very limited applications. Okay, that extended Euclidean algorithm has very limited usage. So if you want you can see, otherwise it's fine, I guess. So next we can go to Sieve. Like it's the most common and most widely used algorithm in the number theory section. It is Sieve of yes, cons. I don't remember the spelling exactly. Let me see. Yeah. So okay. So this is the right spelling. So basically, let's say if you are given a range from 1 to n, and you have to find the minimum factor of every number from 1 to n. How would you do that? You have to find the minimum factor of every number from 1 to n. How would you do this? Anyone? Hello?
Dada, we will iterate, Dada,
Yeah.
we will iterate from I equals to 2 to square root of n, and
Yeah.
the n modulus I when equals to 0, we will just take the value of
Yes.
I
Yeah. So what will be the time complexity for that algorithm?
O of n.
O of?
N.
N. You are
N.
fine.
N.
Yeah, O of n, because what you told that you will run a loop from 2 to root n, and you would check that whether the number is divisible or not, like for every number, right?
Yes.
Yeah, so how the time complexity is O of n, like for one number, how much time it will take, like for finding the minimum factor of one number, what will be the time complexity?
O of 1.
O of 1, you told you will run a loop from 2 to root n of that number.
Yes. To root n.
So how can it be O of 1?
1 second.
Yeah, I have a doubt here. Like, suppose if we have to find the factor of one number, so we can run the loop from 2 to the root of that number. So
Yes,
since here we have to find the factor of every number from 1 to n, so
yes,
for each number we have to run a loop of root n. So will it be n root n type?
yeah, it should be n root n, because for every number we are taking root n, right? And if you have to find for n such numbers, it should be n into root n. So that is the naive approach, but we can do better using Sieve. Okay, so what someone told, he will run a loop from 2 to root of that number, and he will take the lowest factor. So for 1 it will have root 1, for 2 it will be root 2, so on, and it will be for n it will be root of n. So this will be approximately equal to n into root n. Okay, so means this is a naive approach, as he or she told, like I don't know who told. Okay, so next, what I am telling, like we can find the smallest factor in n log n, okay, using Sieve. So what Sieve tells here is that, means what we do here is that, we, let's say we have 10 numbers. Okay, okay, let's say we have 15. Okay, so okay, let's not take the minimum factor, because the minimum factor will be 1 for every number, right? So let's say minimum factor excluding 1, okay, or minimum prime factor, let's say. Okay, so uh, so 1 is not a prime number, okay, so we skip it. 2 is a prime number, okay. So what Sieve tells here is that uh, 2 will divide every number from 2 to n, and we will jump with a length of 2. So the for loop will be something like this for 2. Okay, for 2 we will iterate like this. So the iteration will start from 2, it will end at n, which is 15 here, and the step will be 2, because 2 divides 2, 4, 6, 8, 10, 12, 14. Okay, so see that the difference between 2 and 4 is 2. Again, 4 and 6 is 2. So the difference between the numbers which are divisible by 2 has a difference of 2, right? So if we run a loop from 2 to 15 with a jump of 2, so we will get the numbers which are divisible by 2, right? So is this part clear, what I told just now, like the jumping thing? Okay, so we will start from 2, and we will jump with a length of 2, and let's say we have an answer array where we will store the minimum prime factor of every number from 1 to n. Let's say 1 doesn't have a prime factor, so let's skip it. Okay, so from 2 to n. let's say. Okay. So for 2 we will keep 2. For 3 we haven't find anything, so let's for the time being let it be 0. For 4 the smallest prime factor is again 2. For 5 we haven't found out. Okay, so for 6 it's 2. For 7 we haven't found out. So 8 it's 2. 9 we don't know. For 10 it's again 2. For 11 we don't know. For 12 it's again 2. For 13 I guess. 10, 11, 12. 1 second. 2, 2, 3, 4, 5, 6, 7, 8, 10, 12. Yeah. For 13 we don't know. For 14 it's 2, and for 15 we don't know. Okay. And 1 doesn't have any prime factor, so let it be 0. Okay. So for 2 we will run a for loop like this. For 3 is again a prime number. Okay. So can anyone tell what will be the for loop for 3?
Like 3
Like
to
what?
15, step of 3.
3 to 15, step 3. Exactly. So the numbers will be 3, 6, 9, 12, 15. Okay. So 3 will have a minimum prime factor as 3. Next we go to 6. 6 already has a prime factor which is smaller than 3. So we don't update that because 2 is smaller and we have to find the minimum prime factor. So we don't need to update that. Okay. Next we go to 9. So 9 doesn't have any prime factor till now, so we update as 3. Next 12 again has a prime factor 2, which is less than 3. And since we have to find the minimum, we don't need to update it. Next we have 15, so it's 3. Okay. So next 4. C4 has a prime factor, right? So if a number has a prime factor, which is not itself, of course. So if a number has a factor other than 1 or itself, so it's not a prime factor. So answer 4 is not 0, means it has a prime factor. So 4 is not prime, so we don't need to check for 4 because we are checking for prime numbers. Next we go to 5. Answer 5 is 0, so that means it is a prime factor. So the for loop for 5 will be for I from 5 to 15, step 5. So 5, 10, 15. So 5 doesn't have any prime factor, so it will be updated as 5. 10 already has a prime factor 2, and since 2 is less than 5, we don't care. So and 15 also has a prime factor which is 3, which is less than 5, so we don't need to change that. Okay. 6 is not a prime number since it has a prime factor 2. Okay. So next we go to 7. 7, the for loop for 7 will be 7 to 15, step 7. So it should be 7 comma 14. So we update the answer for 7 as 7. 14 already has a prime factor, that is 2. We don't need to change that. Next 8 is not a prime factor since it already has 2. 9 is not a prime factor since it has 3. 10 is not a prime number, sorry. Then we go to 11. So the for loop will be 11 to 15, step 11. That will be 11 only, and we update 11. Yeah. So next we go to 12, which is not prime. Next we go to 13. So the for loop for 13 will be for I. 13 to 15, step 13. So it will be 13 only, and we update 13. So 14 is not prime since it has 2 as a prime factor. 15 is not prime since it has 3 as its smallest prime factor. So we are done. So we have all the small minimum prime factors for every number from 1 to n. So 2, the smallest prime factor of 2 is 2. For 3 it's 3. For 4 it's 2. For 5 it's 5. For 6 the smallest prime factor is 2. For 7 it's 7. 8 has 2. 9 has 3. 10 has 2. 11 has 11, 12 has 12, 12 has 2, 13 has 13, 14 has 2, and 15 has 3. So we have got the array. So this is the answer array. So can anyone tell what is the time complexity of the algorithm we just followed?
It will be something like this. Like if n is the length of the our
Yeah,
considered range, then it will be like n by 2 plus n by 3 plus n by 5 plus n by 7 plus n by 11. Like this, it will go on up to n by n if it's prime.
yeah, got it, got it. Okay, so let's, for the sake of, so this time is less than this. So this value is less than this value, right? Yes or no? We are taking every number from 1 to 15. Yes or no? Like, is this expression lesser than this expression? Is it true? Yes, because we are adding some extra elements in this expression to get this. For example, we are adding n by 1, we are adding n by 4, we are adding n by 6. So we are adding extra factor, means we are adding extra terms in the left expression to get the right expression. So this value should be less than this value, and this value, you have done this in JE level. What is the value of this expression? Tell me. Means you can means tell an approximate value also if you don't know exactly.
It will be n log n.
Yeah, what will be the base?
Base 2.
2, sure. I
Not
don't think
not the,
it should be 10, right?
I know that it's a logarithm. It's a logarithmic expansion, but I am not sure of the base.
Yeah, like in that series, it should be base E if I am not wrong. Not 10 also, like n log base E. So the expression of log 1 plus x is something like this, if I am not wrong. 1 by 1 plus 1 by 2. 1 second. Log 1 plus x expansion. Log x expansion. Yeah, it should be ln x. Yeah, the base is log of e. Everyone knows what is e, right? So, ln e ln n is 1 plus 1, sorry, 1 by 1 plus 1 by 2 dot 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 plus 1 by n. Okay, so this is a let's say ln. Okay, so everybody knows what is ln, right? So it should be ln equals to log to the log with base e. E is some constant which has value of something like 2.7, like it was in JE syllabus, I don't remember. Okay, so this is the expansion of log base en. Okay, so if we multiply n to this series, we are getting this series, right? Look at this carefully, like we are getting this. So this series, the value of this series is n into log base e n. Okay, So the time complexity of this whole algorithm is O of n into log n, and the base is e, not 2. This is a common question in interview. Like the interviewer can ask what is the time complexity of Sieve, and when you say it's n log n, he can ask what is the base, and if you say it's 2, you will get a negative point. Okay, so remember the base is e. Okay, so is the algorithm clear? So I guess this we are done with number theory. Like this is the most important. Like you can also solve other problems using Sieve, right? Let's say you have to find the sum of factors of every number from 1 to n. Let's say instead of finding the minimum prime factor, you have to find the sum of factors. Okay. Now, how would you do this? Means how would you change? Means modify this? Can anyone tell the algorithm just?
While iterating, instead of minimum, we'll just do like
Yeah, we will add.
ai
Like
plus equals
yeah,
to that number.
and another change we have to make. Can you tell that?
Um, yeah, like for 4, I guess
Yeah,
in
here we have only considered the prime numbers. For some of every factors, we also have to consider numbers like 4, because they also can be a factor, right? So we have to
yeah, yeah.
consider for 4, we have to consider for 6. Basically, we have to consider every number from 2 to n. Okay, so that so the time complexity will be in this case will be, we also have to consider for 1. Okay, so the time complexity will be n by 1 plus n by 2 till n by n, which will be n into log n base e. Okay, so like this you can modify Sieve for these things. Like if someone tells you the sum of factors, you can use this. Or like if someone tells you that find the prime numbers from 1 to n. Okay, so let's the prime numbers will be those whose minimum factor will be whose minimum prime factor will be equal to the number itself. Like 2 has a minimum factor of 2, so 2 is a prime number. 3 has a minimum prime factor of 3, so 3 is a prime number. So like this, the numbers which will have minimum prime factors equal to themselves will be a prime number. So you can find the prime numbers from 1 to n in n log n. So like this, there are variety of applications in Sieve, and 80% of the problems in number theory are solved using Sieve. Okay, so go through Sieve very well. Like you can find the algorithm in CP algorithms or GFG. Like in CP algorithms, there is a nice catalog or nice write up on Sieve, so you can go through it. Also, there is an advanced Sieve you named segmented Sieve. So if you want, you can see that, but I don't think it's necessary. So if you like, if you wish, you can see that segmented Sieve. Instead of n log n, segmented Sieve finds the things in O of n. Okay, so I think we are done with number theory. Factor we have done. So we have learned how to find the factors in root n. We have learned how to find the GCD of a and b in log of maximum a comma b, and we have learned how to use Sieve for various purposes. Okay, and the time complexity derivation of Sieve. Okay, so next we have bit manipulation. Uh, I guess uh, bit manipulation is a more important topic than uh, number theory for from the point of view of interviews. So, like, means which semesters are you in currently? Like most of you,
First.
first. Okay, so You people are comfortable with means do you people know the things like Zor or and or like this? These are three things. Like, do you people
Yeah,
know
yeah,
what
we
is
have been
Zor or
taught. Yes, we have been taught.
Zor? So, like, can anyone briefly explain what are these three?
These are basically like there are some bitwise operations. Like these are gates, or I can say gates. Like if we give give two values, it will give a output like that.
So let's say we have
Value
four
1 and 0.
combinations: 1 0, one. Sorry, 1 1, 0 1, and 0 0. So the Zor will be. Let's say we have three here, or and okay. So 0 0 Zor of 0 0 will be
0.
or. So all
1.
three will be
Yeah, 0.
0.
And will also be
This
0.
one, Zor is 1, odd is 1, and is 0. This one same. This one Zor is 0,
Odd is 1,
odd is 1, and is
1.
1. Okay. So basically, Zor counts the number of Zor counts the parity of the number of ones in a means the numbers we're comparing. So when we have an odd number of ones, Zor is 1. When we have an even number of ones, then Zor is uh, 0. Okay. And or basically when we are calculating or, so when there is at least a single one, okay, so the output will be 1. And for and like every bit should be 1 for the output to be 1. So if at least means if there is a single 0, so the whole output will be 0. Okay. So basically these are the three things that are most commonly used in bit manipulation. So uh, so if you are given the so if you are given a range of 10 to the power 6, so the number of bits will in it will be roughly around 20. In 10 to the power 9, it will be roughly around 30. Okay. So let's say you are given a number 5. So how would you represent that in a binary form? Should be 101. So this is a bit, this is another bit, and this is another bit. So this one is the most significant bit, so it's the MSB, and this one is the least significant bit, that is the LSB. Okay. So so why this is called MSB? Because if the MSB of a number is greater than the MSB of another number, no matter what other the left means the other bits are. Okay, so let me write this. So if let's consider two numbers a comma b. Okay, so if MSB of a is greater than MSB of b, we can always tell that a is greater than b. We don't have to check the other bits. Like, can anyone tell why this is true or why this is false?
Can you repeat the question once more?
The question is this: I am claiming that if MSB of a is greater than the MSB of b, then a is greater than equals to b. Sorry, a is greater than b, not equals to.
Like then the MSB of like it has one bit extra, and this B has one bit. The MSB is 0, so
Yeah,
it will have a greater power of 2 in that place.
yeah.
In,
So why
in
this
that
is true? Because 2 to the power 0 plus 2 to the power 1 plus like this, if we go till 2 to the power n minus 1, so this summation is less than 2 to the power n. Okay. Right? This is right. Means this seems correct to you, this equation. Yeah, 2 to the power 3 is greater than, yeah. So if the nth bit is greater, no matter what the other bits are from n minus 1 to 0, it doesn't matter. So if the nth bit is greater, so the whole number will be greater than a, means the whole number will be greater. Okay. So this is one of the key observations when you are solving a bit manipulation or bit masking problem. Okay. So except this, another application of bit masking is using brute force. Okay. So let's say you are given an array a comma b comma c comma e. Let's say we have this array, and I tell that you have to select some numbers from this such that the weight of the, okay, so such that the numbers you have chosen is divisible, means is divisible by x, and the sum of the numbers which you and the sum of the numbers is maximum. So let's say you have chosen us some numbers, and that numbers be represented by s. So let s be the set of numbers you have chosen. So I am telling that s has to be chosen in such a way that sum of s is divisible by let's say a not a, let's say y. So I have given a number y, and I have said that you have to choose s in such a way that the sum of the elements in s has to be divisible by y, and sum of s maximum out of all such possible sets. How do you do this? Any idea? Is the question clear, like what the question is asking? Hello? Hello? Am I audible first of all?
Yeah, yeah, yeah.
Is the
Yes.
question clear? Yes, so any approach on solving this? Like you have to choose a set of numbers in such a way that the sum of the numbers is divisible by y, and the sum of the numbers is maximum out of all such possible sets.
We will check all the numbers who are divisible by y and just add.
Will that give a correct answer always? Let's say the array is 1 2 3, okay, and y is 3. So the numbers divisible by 3 is 3. Okay, so you will only print 3. But the answer is 1 comma 2 comma 3, because the sum of these 3 is 6, and 6 is divisible by 3. So your algorithm will give a wrong answer. Right?
If the window size is given, we can do it by sliding window approach.
Hello?
Yes, if the set of the number, like the how many numbers is given, like if it is 3 or 4 numbers, it can be
Yeah.
done using sliding window. But if the
Eating
number
window.
of
Okay,
number
okay.
is not given,
Let's say you have only 10 numbers in the set, 10 numbers in the array. Okay, you can even apply a n factorial solution. So how would you do this? Means don't think about the time complexity. Just tell me the algorithm. Yes, Shayok was telling something. Hello.
Generate all possible subsets.
Yeah.
No, that will
Yeah,
be exponential. I don't think
yeah,
so.
yeah. Exponential will work, right? Because the number is only 10.
Yeah, yeah, yeah. Yes. It will be
So how would you
1032.
generate? That's my question. How would you generate all possible subsets?
Like we can either take that element or not take that element.
Yeah.
Like we have two
Okay. So
elements.
the time complexity will be 2 to the power n, right?
Yeah, 10. Yeah.
Yeah. So how would you generate every number? Means all possible subsets. That's where bit masking comes into play. Anyone, any idea?
I have an approach.
Yeah, we
Yeah.
can use
Uh,
recursion also to generate the subsets.
Yeah. That we can use recursion
with
also, but
Right.
recursion
okay,
using
first we'll
yeah, but there's a
uh,
disadvantage using recursion. It uses an extra space. The recursion stack that will be generated will use extra space, and that is a disadvantage. You can definitely
My
use recursion.
approach of 2 to the power n is using recursion only. My means in iterative way it will be a little difficult to generate the subsets. In
Yeah,
recursively, I think it will be easier
using
to generate.
bitmask you can use iterative way. That's my point.
yeah, I have
Yeah,
an
yeah.
Because
Bitmask approach.
Okay. I
because
have an
when you yeah, yeah,
idea
tell.
like if we compare each array position as a bit, then it's like we can either set it on or set it off, like 0 or 1.
Yeah,
Is it okay? Like we can do like something.
yeah.
Yeah, actually,
So
I
uh,
don't know the approach. I can just
okay,
I am
okay, I
guessing
got you, I
like
got you.
the total number of elements that will we take as number of bits, then we'll take a pointer from 1 to maximum number that each can be generated by that number of bits. So in each number, there will be some set bits, and which bits will be
Yeah,
set,
exactly,
we'll
exactly.
take that, we'll
Yeah,
include
that's the
that
approach.
element.
Got it. So somebody was telling recursion. So the problem in recursion is that when you call the function, so recursion will be something like this. So, so if we are using a function generate, and the current uh, array is ARR, so it will be something like this, that you either include the ith element, that is ARR, plus the current element, that is Li, uh, and you uh, call the function with this array, and you call the function without including this, means the current number, right? This will be your recursive approach, something like this, right?
yeah, yes.
Yeah. So
Yes,
the
Bhaiya.
problem here is that when you are calling this, you are generating a recursion stack, right? Like for example, when you are calling this generate, so there will be a recursion stack that will be created, right? Yes or no?
Yes, Bhaiya.
Yeah. So that will use extra
Yes, Bhaiya.
space. So that is a disadvantage. So using bitmask you can remove, means you can solve this problem, and you can generate every subset in iterative way. So like Samit, I guess Samit said that we will iterate every number from 0 to 2 to the power n minus 1, and every number will have some set bits and some unset bits, right? Like, so let's say this is done by I. So the control variable is I. So I will have some set bits and I will have some unset bits. So the first first tell me that how many bits will be there in I, first of all. Number of bits in I.
It will be n.
Yeah, right. So out of n bits in I, there will be some set bits, there will be some unset bits, right? So the places where I has a set bit, we will take those number, and the places or indexes where I don't have a set bit, we will not take that number. So for example, if I is let's say 7, so and n is 5, so the binary representation of I will be 00111. So I has a unset bit in the first position, right? So we don't include the first number. So let's say n is, sorry, the array is, okay. So since I has a 0 in the first index, we don't include 1. Since I has a 0 in the second index, we don't include 2. And since there is a set bit in the third position, we take 3. So the current set will be 3. Then again we have a set bit, so we will have 4, and then again we have a set bit, so we will have 5. So for I is equal to 7, our set will be 3 comma 4 comma 5. Similarly for I equals to, let's say, 12, so n is again 5, so the binary representation will be 1 1 0, and there are two more zeros, I guess. So this will be like this, right? No, this one, because 2 4 8, yeah, this will be the, this is the binary representation of 12. So the set for 12 will be, so we don't include 1 since there is a 0 in front, so then there is a 1, so we include 2. Then again there is a 3, so we have 3, and then we don't have any other set bits, so the set for 12 is 2 comma 3. Okay, so like this we will generate, every possible subset. Like there will, like for every possible subset there will be a binary representation from 0 to 2 to the power n minus 1. So is this part clear, like what I told just now? Every possible subset of ARR will have a binary representation from 0 to 2 to the power 5 minus 1, that is 31. And ARR is a 5 length array. Is this part clear? Means this sentence or this thing
Yes.
is clear, right? Like you can pick any subset and you will see that there is a binary representation from 0 to 2 to the power 5. Like let's say we choose 1 4 5. Okay, let the set be 1 4 5, right? So 1 is included, so first we have 1. 2 is not included, so 0. 3 is not included, 0. 4 is included, 1. 5 is included, 1. So I think this is the binary representation of 19. 1 plus 2, and then we have 16 here. So set 19 will represent this set. So like for every possible set there will be a binary representation of, means from 0 to 2 to the power 5. For example, for set, let's say 1 and 5, the binary representation will be 1 0 0 0 1. This is 17, I guess. So this lies between 0 to 31. Similarly for this subset, let's say 1 2 3 4 5, this subset, for this subset, for this set, the binary representation will be 5 ones, which is the binary which denotes 31 in decimal. For example, if the set is empty, so it will have 5 zeros. So this is the binary representation of 0. So every number is lying between 0 to 31. Observe that. So so every possible subset will be explored if we consider the binary representation of the numbers from 0 to 2 to the power n. N is 5 years, so 0 to 31. So is this clear?
Yes.
Yeah, so like this, you use bit masking to generate all possible subsets. That time complexity is 2 to the power n, but you are using less space complexity, right? Because there is no recursion stack here, so you are using less space complexity. So I think in bit masking you need only this. There is also a data structure called try, but I think that will be a bit advanced for the time being. uh, we have a session for try, if I am not wrong. We can do that. So that is not exactly related to bit masking, but somewhat related. Okay, so but for bit masking, these are the things that are important, like the Zor operations, the OR, and this property that if MSB of A is greater than MSB of B, A will always be greater than B, and this is generating all possible subsets of an array using bit masking. Uh, Also, there is another property. I don't remember exactly. Like A plus B is A or B plus A and B. Okay. So this is another property you can use. Like this is a mathematical addition. Like A plus B is equal to A bitwise or B plus A bitwise and B. So like here you can also see that if this A 0 plus 0 is 0, so this the addition of 0 plus 0 is also 0. Here see that 0 plus 1 gives 1, so 1 plus 0 also gives 1. So here 1 plus 0 gives 1, so 1 plus 0 here also gives 1. So 1 plus 1 gives 2, here 1 plus 1 gives 2. So basically A plus B is equal to A bitwise or B plus A bitwise and B. So this is a important property. So like this property is used in multiple challenges or multiple problems. So like this you can use this property as well. Like I think like this
Is
these are
it
enough for
A plus B equals to A Zor B plus A and B? Like it's a half adder. It gives sums plus carry. I think it will be Zor. Like 1 plus 1, it will be 0 and carry 1. No?
no, we are not taking carry here.
Okay, okay,
Means we are just a simple addition.
okay.
Just let me check once. Okay, wait. Yeah, this is right. Yeah, means we are not taking carry here. We are just thinking about addition, pure addition. Okay, so there is a relation with Zor also, I guess. Like if we take the relation of Zor, it is like A Zor B. This is Zor, right? Okay. Okay, let me write Zor. A Zor B plus 2 into A and B. This is the relation using Zor and AND, I guess. Okay. So basically that makes so these are the few means few properties that will be used. So I think these few concepts are enough for bit masking for the time being. uh, Anyone has any other question? I think we have done for today.
Yeah,
Yeah.
yeah. Could you please tell us some properties of the Zor operator, because there are many questions means regarding the Zor operator. So if you could just give us a few points which
Okay,
we will.
some properties of Zor is A Zor. Okay, like let's say Zor I am denoting as this. Okay, don't think it has an power. Okay, so A Zor A is 0. This is a common property, like because if there are even number of bits, so if you are doing A Zor A, so there will always be an even number of bits for every there will be an even number of set bits for every bit. So A Zor A is 0. So A XOR B is equal to B XOR A because it's commutative. A XOR B XOR A is B because A XOR A will be 0. So basically A XOR 0 is A. Okay. Apart from this, I don't think any other properties are there or any other popular properties are there. This is the most used property actually. A XOR A is 0 and A XOR 0 is A. These two. And
Is there any distributive property? Like there are also a lot of questions where like
yeah, it's
is or
I think it's equal. Like this is equal to, doesn't matter whichever operation you perform first, it's distributive means you can do this. It is also equal to this. So any questions? So like I think there's two topics pretty important, but doesn't have a lot of concepts. Like in DP or graphs, there are a lot of concepts. Okay, so these two things don't have a lot of concepts. Okay, there are a few concepts, and the approaches or the solutions are built upon those approaches. Means those concepts only. So if you know, for example, in number three, if you know the finding the factors and the Euclidean algorithm and the Sieve, most importantly the Sieve, so you will be able to solve 80% of the problems in number theory. Okay. Similarly, for bit masking, it's either some question involving Zor, or it's or some question involving this property, or some question involving generating all possible subsets. Like for the in Google Kickstart, there is a if you are applying a brute force, like for the first subset, the constraints are very low, like it can be 10 or 15. So for that case, you can use bit masking for generating all possible subsets and then solving the question like that. Okay. So any questions from your side, or I think we can end. Like I guess everyone is from IIEST only. Is there anyone outside from IIEST? I guess everyone from our college. So your college is offline or online? Means has offline colleges offline classes started for you?
not
No,
up
it is
till
going
now.
online classes, but our end sem will be offline.
Yeah,
I
from
guess
April.
and sem
For
which
the
will also be
second years,
online.
I think our college will. For the second years, I think it will start in offline mode from 4th of April.
I don't think so. Like because there has been a petition signed by the GS General Secretary of CST. I think you have got that. Like
Yeah, yeah, yeah.
they are.
But
I think it should be online. Like let's see. Okay.
yeah, as
So
of
any
now, means the official announcement we have this
yeah,
letter if
I
it is.
know, I know. For second years, I know that it is opening from 4th April.
Bhaiya, I have a question.
Yeah,
Hello?
yeah.
Yeah, I was asking that what is the efficient approach for generating all the subsets, all the sets?
This is the for generating all the subsets. This is the most efficient. If you tell every subset, because there will be 2 to the power n number of subsets, so this is the best approach.
Okay, we got it.
So any other questions, or I think we can end. Like I will wait for a minute if there is a question or not, and then we can end. Okay, so I think
Regarding
we can.
that question,
Yeah,
uh,
tell.
sum of is that question. We are how are you solving the question?
if you are
Like after
generating every
generating.
subset, right? If we are generating every subset, so if we know the subset, we can easily find out the sum of the subset, and we will check that whether the sum is divisible by y, and if it's divisible by y, we will update the maximum answer, right?
Yeah. Okay.
Yeah. So any other questions? Okay, so no, since no one has any other questions, I think we can end. So bye everyone.